This is Learning Assessment Problem 7.3. This circuit contains an inductor and a switch which opens and disconnects a 12-volt source from the circuit at time equals 0. So we have a switch opening process as well as an energy storage element, the inductor. We're asked to determine the function I1 of t for t greater than 0. We'll use the differential equation approach to solving this transient problem. For the inductor, we'll be concerned about the inductor voltage V sub L, the current I sub L. We note that I sub L is the same as the current I1 that is the goal of this problem. So we'll determine the initial condition for the I1 current, which is the same as the initial condition current in the inductor. So for t equals 0 minus, we'll assume that the circuit is in the steady state and that the voltage across the inductor at 0 minus is equal to 0. So a DC type of analysis will give us that I1 of 0 minus will equal 12 volts divided by the 12 ohms in series with the inductor, and this is equal to 1 ampere. We're going to use the concept that the inductor current, which is the same as this I1 current, is continuous across the switching episode, so we can say that I1 at 0 minus is the same as I1 at 0 plus, and that's again 1 ampere. So that's the continuity of the inductor current, which provides that concept. So that continuity of inductor current is the principle used there. So now we'll consider what happens for t greater than 0. The circuit now with the switching operation occurring and removing the voltage source from the circuit. We have the remaining circuit. 6 ohm resistor, 12 ohm resistor, the 2 Henry inductor. V sub L now will be a consideration for the inductor. And we have this I1 of t. So we can consider KVL around this closed path. We'll have induced voltages across the 2 resistors plus the inductor voltage to sum in this KVL equation. So we have 6 ohms plus 12 ohms times I1 plus V sub L sums to 0. Now V sub L of t for the inductor is equal to L di 1 dt in terms of the current which we seek. So therefore our KVL equation becomes 2 di1 dt plus 18 I1 equals 0. So this is a differential equation. We'll assume the solution of the form I1 of t is equal to K1 e to the minus t over tau. We think for a moment about what's happening in the circuit. We've charged the inductor, so to speak, stored energy in its magnetic field when the 12-volt source was connected to the circuit. Now that energy will be dissipated in this loop, and eventually the current will fall to zero as the energy is lost in the heat of the resistors. Let's think for a moment what happens in this circuit after the switch opens. The energy which was stored in the magnetic field of the inductor begins to be dissipated in the two resistors in this loop circuit, and eventually the current will fall to zero. So this type of assumed solution will provide for that behavior. So we can substitute this expression into our differential equation, and we have 2. The derivative of that exponential relation gives us a minus 1 over tau k1 e to the minus t over tau plus 18 k1 e to the minus t over tau is equal to 0. All of this cancels out, and we have that the time constant is equal to 9 seconds. We know from our calculation of the initial condition, we have I1 of 0 plus is K1 in our assumed solution, and we've determined previously that this is equal to 1 ampere by the continuity of the inductor current. So we have now that I1 of t is equal to 1 e to the minus t divided by 9 amperes for t greater than 0. As a matter of interest, you might consider KVL around the loop for t equals 0 plus to determine V sub L at 0 plus.